Okay, perfect. All right, so it's my great pleasure to introduce Dr. Zhao. So he's a professor at the University of Illinois at Urbana-Champaign. And then some of you may not realize this, but he's an alumnus from Ohio. So he did his master's degree here. And so it's a great honor to have him come back and share, I guess, his most recent work. Now, Han has done some really interesting work across a number of areas. I mean, this was true, I get research here, and then after that at Carnegie Mellon, where he got his PhD. And I read as well that you're now an Amazon visiting researcher. So I guess there's probably some more to be said there about interesting research with Amazon. But I guess today your expertise is quite broad, but you'll tell us about perhaps some really interesting things regarding fairness and optimality.
Yeah.
Okay, so please go ahead.
Thanks, Pascal. It's really my honor to be able to come back, and always nice to see old friends, and as well as Pascal. I worked with Pascal during 2014 to 2015. At that time, mostly working on probabilistic graphic model, and later, more recently, I'm going to talk about some recent work in my group, mainly working on the trustworthy side of machine learning and AI models. And in particular, today's topic will be mainly focused on fairness. So in the sense that we will understand what's the typical definition of fairness in the literature, and is there any trade-off between fairness and accuracy, and if there is, how to achieve the so-called optimality. Okay, so we see that I probably need to, for this audience, I don't need to repeat the success we've seen in the past decades of using machine learning in real-world applications, and particularly in a lot of high-stake applications. For example, if you think about student loan application, in nowadays, a lot of scenario is each individual will fill an online form. So regarding your background and your personal information, and this kind of online form will be used, feed into automated decision-making process. And then at the end, the automated decision-making process will try to decide whether to approve or decline loan. Right, so that's just one example of showing the applications of machine learning. But beyond loan application, it has also been used in business like a credit scoring, as well as in Amazon. Amazon has an automated pipeline to take the PDF version of resume as input, and then using some OCR technique to transform the PDF into the so-called description. Is essentially a feature vector includes what's your education history, what's your past industry, as well as academic experience, and then go through another typical pipeline to decide whether try to extend an interview to the candidate or not, right? Now, in those cases, we want to make sure that our algorithm or our end-to-end model is fair. So I will explain what does that mean to be fair. But you can imagine that if there's some historical bias exists in the data set where we use to train our model, then if we do not take enough care to curate those models, then this model will inherit the existing bias in the data set. So one question is, how can we use algorithmic intervention to remove or prevent the models trained by machine learning to inherit or even exacerbate the existing bias? And one particular definition of fairness in the literature is called statistical parity. And it's also known as demographic parity in the literature. So let me explain what does that mean. So here, y hat corresponds to a prediction model. So you can imagine we have some X typical description about each individual's input, and then you can build your favorite model like decision tree, random forest, or neural nets. The output of such model will be y hat. So y hat is your prediction and try to be as close as possible to the ground truth label y. But in those scenarios, I also have a protected attribute. And then you can imagine, for example, in student loan application, I want my loan approval rate to be independent of whether the individual is from the male or female group. And then you can imagine here the A corresponds to a group membership indicator. So in the simplest case, it only takes two values. Say one of the either is from majority group or from the minority group. And in the case of loan application, I just mentioned about A can take, say, the gender attributes, say male or female. And the criteria of statistical parity essentially say that I want the outcome of my model to be statistically independent of the sensitivity attribute or the protected attribute. So in words, that just means under this definition, algorithm is called fair if and only if it does not use any information. So when I say information, I mean information theoretical sense. You can understand the mutual information between the outcome of your decision-making model and the protected attribute is 0. Right. So if this is true, that just means the model is not using any information related to the sensitivity attribute in the decision-making or prediction process. And this definition is actually not new in the literature. Actually, it's already like invented before people get to know the importance of algorithm fairness. And at least back in 14 years ago, this kind of criteria is known as independence criterion. Basically, we want to be a classifier that satisfies certain independent condition with respect to a predefined attribute A. So let's see a real world example. So a famous example in the United States is this summer, actually more specifically at the end of June, the Supreme Court in the US, they made a rule. So the rule basically is regarding college or university admission for undergrads. And they basically say that in order to make sure and the whole process is a notion of fair, they try to remove a particular sensitive attribute, in this case is the race, from being used as input explicitly to any decision-making process, no matter whether it's like automated or it's like a manual decision-making process. So essentially say that they try to at least achieve this goal of saying that decision-making is being independent of the race attribute. And we can try to, at least intuitively understand this kind of rule is trying to enforce or achieve this kind of criterion. But one natural question we want to ask is this kind of like a fairness through blindness sufficient? And I say whether it's sufficient is, abstractly speaking, what the rule suggests is, suppose originally we have a classifier, let's call it C, and the C will take both the description about individual, let's call it X, as well as the sensitive attribute A as input. And now the rule basically says that you cannot take A explicitly as part of your input. And then let's try to build a new classifier or decision-making rule, which only use X, right? So in the context of like a criminal justice, you can understand, I want the decision from a justice system to be independent of the race. Now, what if I just remove the race attribute from my input? So my question is, do you think it's sufficient to achieve the goal? Why?
Well, so other attributes could be correlated with
race,
and as a result, it's not completely.
Yeah, exactly. So that means even if we just explicitly remove the race attribute from the input, it's not sufficient to achieve the goal of like independence or mutual information being 0. So as just Pascal has just mentioned that, although I remove race explicitly from the input, there could be other attributes which are highly correlated with the race attribute. And this problem of phenomenon is known as the redundant encoding issue. So that means implicitly, the model, even without explicit access to the race attribute, can use other attributes in the input to reconstruct the race attribute and then try to use it in an implicit way. And in particular, in this example, we can see, at least in the United States, zip code is always highly correlated with the race attribute. And also you can try to get a sense of the race from the last name. So if the last name is used as part of the input, that's also will cause a problem, right? So now, since this kind of rule, fairness through blindness is not sufficient, so we wonder what kind of practice we can use in those high-stakes applications to achieve the goal of statistical parity. Now, before I introduce the mechanism, so I will give a brief overview about typical machine learning pipeline. So typical pipeline is for example, in the case of, say, loan application, we have a group of applicants. And then each applicant, we can describe it into a feature vector. So the feature vector includes, say, the age, education, race, gender, income, credit score, etc. And then such description will go through a black box. So here the black box is, you can understand, is your favorite machine learning model. Doesn't matter whether it's it's a complicated neural net, so it doesn't matter if it's a simple linear model. So here we just assume it's a binary classifier for simplicity. And then after black box machine learning model, we have a prediction. So whether the model thinks we should approve or decline a loan, right? So technically that means we start from a tuple. The tuple contains 3 attributes. So here X is our input description about each individual. And then A corresponds to the protected attribute or the sensitive attribute we try to be fair with respect to. And then Y is the target variable. So here target is say whether I should approve or decline the loan. And then once we have this tuple, draw ID from some underlying distribution D, we try to build a classifier F, and the classifier F can be say any of your favorite model. And once we have the classifier, we get some prediction Y hat. Right, so Y hat is my final outcome. So supposing the normal context in supervised learning, if you don't have any fairness constraint, so your goal is to make sure your model is strong enough so that Y hat is as close to Y as possible. So that's the only goal we're trying to achieve. But nowadays, under the statistical parity constraint, so beyond the accuracy criteria I try to preserve, I also want my algorithm to be fair in the sense that I cannot take any information related to A in the decision-making process, okay? Now, since we are familiar with the whole typical pipeline as well as the setup of the problem, let me introduce at least 3 different kinds of methods to achieve this goal. So the first one is a very popular and also widely used paradigm. It's called pre-processing. So the idea is that, okay, so if the original data, the raw data we are given can contain some potential bias or correlation related to the sensitive attribute, so why not we do a data pre-processing or filtering process so that after the filtering process, the new feature does not contain any information related to A, right? So we know one attempt we just talked about, just removing A directly from the input is not sufficient, but that's a very naive pre-processing method. I can use much more complicated version. In particular, one way to achieve this goal is called the so-called learning fair representation. It's a representation learning paradigm or feature learning paradigm. And the idea is also quite intuitive. It basically say that we're given a data set, and once given a data set, I partition all the applicants into 2 groups, conditioned on the sensitivity attribute. For example, in this case, I have 2 groups, corresponds to all the male applicants and the female applicants. And then for each group, I sample a batch of data and ask them to go through a feature transformation here. So a feature transformation here, you can understand as your favorite neural nets or other kernel methods. It doesn't really matter. But as long as a feature transformation have an encoding of the data, and then at the output of the encoding, I will simultaneously train the so-called discriminator. Or in this context, you can understand to be an auditor. And the job of the auditor is very simple. So once given 2 samples of data, one from each group to the auditor is asked to answer the following question. Can you correctly guess which sample comes from which group? Right, the idea is that I will simultaneously train the auditor as well. And if I can confuse or for a potentially very strong auditor, in this perspective, I can say that my feature does not include any information related to A. Any questions? Okay, so although the description here is very ad hoc and intuitive, but we can make all the arguments very precise mathematically, but I will skip the detail here. But roughly speaking, that means if we try to find feature and the feature still contains information related to A, this kind of information will be utilized by the discriminator to give an accuracy strictly larger than 0.5. Now at the equilibrium, I want that no matter how strong the discriminator is, it cannot answer this question accurately, say more than a random guess. Then from this perspective, I can say my feature does not include any sensitive information. Okay, great. So if we think about the whole process, there's some prerequisites in order to apply this procedure. So the first is, since I train all the components, including the feature transformation, as well as discriminator from scratch, then the whole model need to have full access to the tuple X, A, and Y, meaning that it will have raw access to data X, as well as the sensitive attribute, and the ground truth label Y. And also in practice, this kind of adversarial training, it's called adversarial training because it's solving min-max gain, can be very numerically unstable in the sense that it's hard to converge, especially in the context of using neural nets, which are nonlinear model to instantiate both the feature encoder as well as the discriminator. Now, if we look into a little bit detail about or give a illustration about how this algorithm works, it's essentially say, I have 3 components in the whole training paradigms, one encoded for the male group, one encoded for the female group. They can be shared or have group-specific encoder, that doesn't matter. And the third component is the discriminator. Now, once I have the 3 components, if you're familiar with the generative adversarial nets, the encoders will compete against the discriminator, and I will train the whole procedure end to end. So at the end, ideally or theoretically, at the end of the training, when equilibrium is reached, then the feature will not include any information related to A. And in this way, we overcome the previous limitation, say, just to remove the sensitive attributes, because using this paradigm, all the other related attributes, which have any correlation or mutual information with the sensitive attribute, will also be removed in the whole process. Okay, so that's the first part of the solution. The second paradigm is called in-processing. And this hopefully seems like more familiar to machine learning people, because it's usually try to transform the original problem into a constraint optimization. So recall here, we usually have 2 goals. The first goal is I want my model to be accurate, in a sense that if I use F theta to denote my model, and I say the cross-entropy loss on mean squared error of this prediction model is going to be small. So that's my objective, right? Suppose without any fairness constraint. Now, if I have a fairness constraint, I can just use encoded constraint itself as a part of the optimization process, meaning that, statistical parity basically say that the decision-making process does not use any information related to A. And equivalently, let's say, if I condition on a different value of A, then the loan approval rate in the application of student loan application should be the same across both groups, right? Because if they are not the same, then the model is implicitly using information related to A. So on the other hand, if there's no information being used, then the loan approval rate should be the same, so that I can measure what's the loan approval rate between the 2 groups, and I want the difference to be small, less than epsilon. This is called in-processing because we directly encode our constraint into the formulation of optimization formulation. But one potential cons of this approach is, again, we need full access to all the data because we are training a model from scratch again. And then what's more important, which potentially worse than the pre-processing approach, is we need to design a dedicated optimization procedure for different model F. For example, if we start with linear model like logistic regression, then this problem has a very nice convex formulation. We can solve it using any off-the-shelf convex solver. But now if we instantiate F to be a nonlinear model like neural nets, then the problem becomes much more complicated, and we need to resort to, say, a stochastic gradient descent or other stochastic optimization algorithm to try to achieve a station point. And what's more important, especially nowadays, is if you say want your model to be very powerful and potentially using a very large-scale language model, then realistically speaking, you cannot train your language model from scratch in order to achieve the fairness goal, right? Because we don't have such large number of GPUs to train, say, 170 billion model from scratch, and you may not have even access to the data used to train the ChatGPT model. So although theoretically speaking, for small scale problem, in processing is also very useful, but when it comes to large scale model, it's not going to be applied in practice. So the third paradigm, which is the main focus today, is called post-processing. So let me make a comparison of the post-processing paradigm versus the pre-processing and the in-processing. So post-processing assumes that we are already given a very strong and accurate model, say a black box, as your prediction model. And this model can be biased in the sense that it does not satisfy the fairness constraint, but that's fine. So my only requirement is this model is very accurate on the overall population. And now, so recall this is a typical machine learning pipeline. And then instead of just to follow the original recommendation, approval or decline, I will say do not just to follow the original suggestion, but I will put the original prediction from the black box model into a post-processing procedure. So here the capital A denotes the post-processing algorithm. The algorithm will take the outputs of your black box accurate model as input, and also take the sensitive attribute as another input. So that after the processing of this algorithm, it will produce y tilde. So y tilde is different from y hat in general. But I try to make sure that y tilde is accurate on one hand, but more important on the second hand is going to be fair. Okay, so if we follow this paradigm, at a high level, you see that we do not need to have full access to the original training data. Because the training time, the data is only being used to train your black box model, the data can be dropped or just hide from after the training process. And then during the inference time, I also do not need to directly have access to your training data. I only need to have the query data X. And then I just apply the black box model as a first step to get the query results. Query result is always easy to obtain. For example, even for large language model, you can always buy a OpenAI API and then use the API to send your query to ChatGPT or even GPT-4. Then once you get the forecast from the model, I will just put the forecast as well as A to go through the post-processing procedure. So that means we do not need to train everything from scratch. So that's a good part. And second part is you do not need to know what's the details about your black box model. So the only assumption here is the black box model is accurate. So I will make this assumption more precise later, but for now you can understand the assumption is your black box model is strong, but can be potentially unfair. Okay, any questions so far about the paradigm? Yeah.
Yeah. So if I understand this correctly, in the last step, there is no fairness element being brought in during training. It's only after during execution.
Right. During training, you don't need to care about fairness. You just try to achieve accuracy as much as you can. And then once you get a very accurate model, the accurate model will be post-processed by this algorithm.
Okay. And just to be clear, like after training, are you applying the model to a data in the same distribution or is it a out of distribution?
It's the same distribution. Yeah, it needs to be the same distribution. Right.
So what is that X? Is it like a logis or just like a label?
It's a label.
It's just a label.
Yeah. For the simplest case, just a label. But for the general case, it needs to be the logins. Yeah.
So when it is A, the sensitive attribute A, is it included in X?
A is not included in X.
Okay, then so now you're using X in the black box classifier, and then you're using A for the post processing.
Yeah.
So whatever reason that you don't need to have full access to X and A.
Oh, because this step does not need to have access to X. I only need to have access to the prediction of X.
Oh, okay. You mean for the post processing?
Yeah. Yeah. And for example, so usually in this process, there are two agents. One is the black box vendor. Their goal is try to make the model as accurate as possible, and they have the full access to all the data. But the fairness part is administrated by another agent, and the other agent is to make the model fair, maybe due to legal regulation. But this part does not have access to the original training data if they want to do the fair process. So that makes the data sharing a little bit easier to the two parties. One is a trusted agent, which can use the original raw data to build an accurate model. And the fairness part does not need to have access to the original data. Okay, great. Now, before I talk about the concrete algorithm, I do want to draw a little bit of attention here. So the title is called fair and optimal, but so far we haven't talked about what do I mean by optimality here, right? So the reason why we have optimality, because whenever we add fairness as a constraint to a supervised learning problem, then in the worst case, you can expect it's going to be a drop of accuracy. Because the original problem, it's unconstrained optimization. You have a whole search space. So you can choose whatever hypothesis class you want to use and choose the best one to fit your model. But now here we have a fairness constraint that essentially limits the search space. Say that the set of hypotheses you can use for your model. So in the worst case, you would imagine there's a drop of accuracy. And we want to understand what's the precise price we have to pay in order to achieve fairness. And once we have a better understanding about what's the precise price, then we can talk about optimality in the sense that if we can construct an algorithm to achieve the least amount of price, then that's going to be the optimal fair classifier we're looking for. Okay, so now here, that means we have answered two questions. So the first question is a quantification about what's the notion of price in the context of fairness. And the second question is, if we know what's the price, how can we achieve it in the optimal way? Cool. Now, so let me just give a very simple extreme example to illustrate that in general, you would imagine there's a drop of accuracy, or there might be a trade-off between fairness and the utility or accuracy. So to see this, let's consider a very simple example. Say, what if in the underlying distribution, your target label Y is fundamentally independent of the sensitivity attribute A. So this can happen, for example, in long application. I can instantiate the meaning of variable A to be whether I like watching movie or not. And whether you like watching movie or not has nothing to do with whether the bank should grant a loan application to you or not, right? So in this case, then the ground truth label Y is originally independent of A. Then even if I add this fairness constraint into your process, you can imagine there shouldn't be any trade-off because your target is to predict a totally independent attribute of Y. So in this case, there's no price. But in the other extreme example, for example, the target you try to predict is precisely the attribute you try to protect. In this case, so for the goal of prediction, you want to make accurate prediction with respect to Y. But for the fairness constraint, say you cannot use any information related to Y because Y equal to A. So in this case, you can imagine you cannot do any prediction. So you shouldn't be able to achieve an accuracy, say, significantly larger than 0.5, right? Because the fairness constraint asks you to not use any information related to Y in this case. So if there's such a trade-off, that means there should be a term that quantify the dependency of Y and A. And this kind of like dependency or trade-off should be inherent. So what do I mean by inherent? That means it does not depend on any specific algorithm you are going to use to build your classifier or achieve your fairness. And it shouldn't matter whether you are, say, your algorithm is polynomial time or exponential time, say how many computational resources you have. And it should not depend on how large your sample size is. So that means it should be information theoretical trade-off, right? Because it only depends on the underlying joint distribution. It has nothing to do with the computational resources, the sample complexity or sample size, or any specific algorithm we're going to use. So it turns out, indeed, there's such a lower bound, and the lower bound is very simple intuitively. It basically says that if you want to achieve statistical parity, in the sense that your outcome is independent of A, then no matter what kind of algorithm H we're going to use, then if I look at the sum of group-wise error, so what do I mean by that? So if we look at the inequality, then it contains two terms on the left-hand side. The meaning of the first thing is the ground truth 0, 1 error on group 0. And the second term is the ground truth 0, 1 error on group 1. And I say, if I take the sum of these two errors, then it has a lower bound. And the lower bound is the meaning of the difference of base rate. And if we look at the expression of the difference of base rate, you see that's essentially the difference of the ground truth conditional probability for y across two groups. And notice that this term does not depend on your sample size. It only depends on the underlying distribution. And this number is a number between 0 and 1. If you're familiar with causality, this is also known as the average treatment effect. If you try to interpret A is the control variable and Y is the target. So that's the that's the form of the trade-off. But the implication is that in the worst case, if you want to be a fair algorithm, and if the difference of base rate is large, then no matter what kind of algorithm you're going to use, you have to make a large error on at least one of the group. Because the sum of the two error has a lower bound, that means at least one of them has to be a large error. Okay, and now let's try to make sure this term is actually sensible in the sense that it's reduced to the two extremal case we discussed before. Now let's see what if A equal to Y. So if A equal to Y, intuitively that means your algorithm cannot use any information related to Y for predicting Y itself. So that's a very bad situation for prediction. In this case, the difference of base rate is 1. That's the two conditional probability, one of them is 0, the other is 1. But if the low bound is 1, so that means at least the maximum error, group-wise error is 0.5. That's actually very bad, but it's consistent with our hypothesis, right? Because if the largest error is at least 0.5, that means on at least one of group, you cannot do anything better than just the random guessing. On the other extreme, if A is independent of Y in the true distribution, then you see if A is independent of Y, the conditional probability reduces to the marginal. So they're the same. The low bound is 0. So if the low bound is 0, there's no price we have to pay in terms of fairness. That's also consistent with our intuition, right? So that means the difference of base rate is a fundamental quantity that characterizes the coupling between the sensitive attributes as well as the target variable Y, right? And you may wonder, so why we care about this specific form of error lower bound? Because usually, if you're interested in a machine learning problem, instead of looking at the sum of group-wise error, usually people care about the joint error. The joint error is different from the sum of group-wise error because the joint error is a weighted sum of two groups, and the weight depends on the relative population of the two groups in the overall distribution. But once we have the lower bound for the sum of group-wise error, you can naturally get a lower bound for joint error as well. And this is the derivation. But if we make a comparison, we can see why we should use the sum of group-wise error rather than the joint error as a measure. It's because the joint error is also influenced by the imbalanceness between the two groups. So that means if we use the joint error, we can have the disguise that the joint error is very high, even in the fairness constraint. But that doesn't actually mean fair because the joint error is biased towards the majority group. So in the worst case, if the majority group takes over, say, more than 99% of the overall population, then you can just bias all your prediction to the majority group. In this case, you do not sacrifice accuracy because more than 99% of the population comes from a majority group. So that means your joint error is going to be small. At the same time, you also have the fairness criterion because you just use the same decision rule to both groups. And the decision rule is based on the majority group. That's the reason why if we want to get a lower bound for the joint error, the lower bound must contain a term. So the term essentially characterizes the imbalanceness between two groups. This is also known a notion of entropy. It's just not the Shannon entropy. It's called the 0-1 entropy in the literature. But it's a measure of the uniformness of the overall group-wise population. Okay, now let's use a single figure to make sure, at least to illustrate or convince you that the result we have is correct. So if you think about the problem setting we start with is we have two distributions, D0 and D1 corresponds to two group-wise distribution. They are different. Because in general, the group-wise characteristics will be different. So each circle here corresponds to a collection of distributions, and each dot corresponds to any specific distribution. So that means we start from two specific distributions. And then we're training an algorithm. So in general, the algorithm can also take the sensitivity attribute A as input. So that means the algorithm can be group specific, meaning that for each group, you have a different predictor. And now once you have such a predictor, they are naturally induced to outcome distribution over the label space one. So this circle includes the fraction of distribution over y. And then because we apply to predictor, I got to predicted distribution. But if we look at the second circle, beyond the two predicted distribution, you also have the two ground truth distribution. That's the true label distribution. And these 2 points are constant because it only depends on the underlying joint distribution. It has nothing to do with what specific kind of algorithm you're going to use. But if we see the quadrilateral formed by those 4 different points, if we choose a proper metric, and you know that by a simple triangle inequality, the sum of the 3 dotted lengths is low bound by the solid line. That's just a simple triangle inequality. But the solid line is a constant. The length of the solid line is a constant. And that's precisely the difference in base rates. Because these 2 points are fixed. There's nothing to do with the choice of the algorithm. But I can fairness guarantee or constraint say that the 2 predicted points should be overlap with each other. Because you want the same approval rate for both groups. So that means the 2 predicted distributions should coincide with each other. And now the distance between the 2 black dots and the 2 red dots is further lower bounded by the error rate. And combine everything together, you know that the sum of the error, group-wise error is lower bounded by the length of the solid line. So hopefully that's just a intuitive argument to convince you that you would naturally expect this kind of trade-off to happen in general. Now, once we talk about the trade-off, the natural question is, can we actually construct an algorithm to achieve the trade-off? So why this problem is important? Because if we can indeed construct an algorithm to achieve the lower bound, then that means our inequality is tight. So that means that the price we have to pay is tight. At least can be achieved in certain cases. The second one is that also means that the algorithm we're going to construct that achieves the lower bound is the optimal algorithm, right? Because no matter what kind of algorithm you're going to design, it has to satisfy this inequality. And if we can design such an algorithm that achieves the inequality, so that means the algorithm is optimal, right? Okay, so now let's see how can I construct this algorithm. But before we talk about the construction, I want to point out one observation. The observation is that the problem we're going to solve is hard. Why? Because here we have 2 constraints. I want to be optimal and I want to be fair. So this is strictly harder than, say, not necessarily strictly harder, but not easier than, say, I just want to achieve the optimal classifier itself. But achieving the optimal classifier is known as learning the base optimal classifier. This problem is hard in general. So that means I cannot solve the problem from scratch. So I have to take some oracle assumption. So the oracle assumption is I assume I start with a very accurate classifier for each group. And more specifically, I have access to the base optimal classifier for each group at the beginning. And then here I will skip this part. The part basically is formalized that our problem is not simpler than learning the base optimal classifier itself. But the more interesting question is, suppose we have such oracle access, meaning that I start with group-wise base optimal classifier. How can I use them to construct the optimal fair classifier? Okay. And now the pseudocode is very simple. I will explain, so do not be scared about this part of the code. And the only thing we need to remember here is that we start with oracle access to H0 star and H1 star. They correspond to group-wise optimal prediction potentially unfair. And I also compute two quantities. That's what's the probability label equal to 1 across different groups. So those are the only 4 quantity I need to use. And without this generality, I can assume alpha is at least as large as beta, right? So that's fine. And then once we have this for the post-processing procedure, it's like a decision tree. Okay, so that's a very simple procedure. Let me explain what does that mean. So during the inference time, so whenever we receive a query in the form of X and A, then I'll first check whether it's from majority or the minority group. If it's from majority group, say equal to 0, I go through the left branch of decision tree. And later we'll talk about the other part. Now, if we go down the decision tree, I will first call the group-wise optimal decision rule and see whether it's prediction 1 or not. If it's prediction 0, I just follow the prediction. If it's predicting 1, I'm doing a randomized prediction. So what do I mean? So if it's predicting 1, then with probability alpha plus beta divided by 2 alpha, I will follow the suggestion. Otherwise, I will flip my prediction. Okay, so that's the structure of the algorithm. For the other branch, that's symmetric. So for the minority group, I also call the minority group wise based optimal predictor. And if the outcome is 1, I follow the prediction. But if the outcome is 0, with certain probability, I follow the prediction. With other, I flip the prediction. The only difference is the specific choice of flipping probability is going to be different between the 2 branches. And in fact, we designed these 2 probabilities to make sure the fairness is true. The fairness criterion will hold. Okay, any question about the procedure itself? Yes.
Is this something like projection sampling?
Projection sampling?
Sorry, rejection sampling. Computations.
It's not exactly the same. Rejection sampling, you will just say whether you design a threshold, and you always, with certain probability, you always accept or reject, right? But here we are conditional version, say, depending on which branch it is, and depending on what's the original outcome. It's a randomized outcome. Yeah.
So like, does it mean that whenever you are flipping the decision, you are actually making an error?
Yeah.
Because this is an optimal classifier. Right?
Yeah.
So basically, you are kind of like artificially introducing errors to the classifier.
Right.
Okay.
That's true. In order to achieve fairness.
In order to.
Yeah.
Like depending on the kind of fairness you want to achieve, right? So there's some epsilon that you want to have between the 2 different distributions. So shouldn't that epsilon somehow appear in this decision rule?
This is the exact version.
So epsilon 0.
Epsilon equal to 0. But you're right. If you allow epsilon to be strictly non-zero, this term will, the flipping probability will be smaller for this side and the smaller for this side.
This is also generalized to like the attribute which are non-binary.
Yeah, I will talk about that. That's a little bit harder. So that's the reason why I first talk about this simple case. Okay, so if we follow this type of algorithm, we can actually show 2 properties of it. So the first property is it's indeed fair. It's very easy to verify. But on the other hand, perhaps more importantly, it's the optimal one, meaning that if we construct a classifier in this way, the lower bound is achieved. Okay, so that's great. So that basically answers the second question. Say, is that possible for us to construct an algorithm to achieve this goal? But we do have an assumption. The assumption is the original problem is realizable in the sense that if you don't have any fairness constraint, you can achieve 0 error on each group. So there's no underlying noise. So that can also make sense because if there's some underlying noise, then no matter whether you have fairness constraint or not, you cannot achieve 0 error. So here the low bound is high because this low bound is purely the price we pay due to fairness constraint, not due to the underlying noise of the data. So that means the algorithm works for the noiseless setting. But more importantly, and here some observation is, we can actually show if you want to achieve the optimal fair classifier, it has to be randomized. So in a sense, if we go back to this graph, you see it's possible that with the same X and A, you get different outcome. So that's a randomized classifier by nature. And that's necessary. And you can show that, we can show if you restrict yourself to deterministic rule, you cannot achieve fairness, because in the worst case, it's possible within each group, you only have one X. So all the attributes share exactly the same value of X. And if that's the case, if we restrict ourselves to deterministic decision rule, you cannot try to balance the approval rate between the two. Okay, so that's the first comment. And the second comment is that we also show the problem for learning the optimal fair classifier is not much harder than learning the base classifier itself, right? Because originally we say our problem is not easier than learning the base classifier because we have a further constraint. And now with the post-processing step, you see that as long as you have Oracle access to the base classifier group-wise, then you can also get the optimal fair classifier. So the complexity of this problem is the same. Okay, great. Now let's go to the more general setting. So the first extension is we do not start with just two groups. You have multiple groups and multiple class. But again, let's for now assume noiseless, meaning that the price we have to pay purely because of the fairness constraint, not because of the hardness of the problem itself. Now in this case, the bad news is we don't have any nice analytical solution to characterize the price, but instead the price is given by the optimal value of this problem. The problem is called the TV-barycenter. Here TV means the TV distance. TV distance is equivalent to L1 distance, so that's the reason why it's called TV. And we're solving for distribution Q that minimizes this value. This is efficiently solved. It's a linear program due to the L1 distance. But geometrically, what does that mean? That means, first, before talking about geometric intuition, I want to say that the optimal solution of this linear program is going to be the price. So we can generalize our previous theorem to this case. It's just that the generalization is not analytical. In a sense, we don't have an exact solution, but it's the optimal value of a linear program. And more importantly, geometrically, that's a very intuitive solution, because if we have a multiple class, then each class-wise distribution over Y is a point over the probability simplex. And now the problem is originally the true label distribution Y for each group are different. So we start from, say, if we have 5 groups, that means we have 5 points over the probability simplex. But the fairness constraints say that you cannot have different prediction probability for different groups. We only need to use 1 point. So I want to find 1 point Q over the probability simplex, and that's going to be the predicted probability for fairness. But at the same time, I want to ensure optimality. So that means I want the distance between the new point Q star to minimize the sum of all the pairwise distance to the original P. And we can show that the distance between the Q and P is precisely the price we have to pay for each group in order to achieve fairness. And that's the reason why the optimal solution is given by a linear program, and the distance matrix is L1. Okay, great. So that hopefully give us the intuition how to extend this approach, but the linear program can be efficiently solved. And once we have the linear program solution, we can construct the same randomized algorithm to achieve optimal fairness. It's a straight generalization. Okay, so the last extension, which is solve the most general problem, is we have multiple groups, multiple class, and the data is noisy. I mean, in the sense that it's not realizable. Even for the base optimal predictor, the error is not 0. It's some positive constant, right? Because that's the most general case. And turns out, in this case, we need to slightly restrict our Oracle access. In the previous 2 cases, in the noiseless setting, I don't need to have access to the base score. I only need to have the base classifier, which is the label itself. But in this case, I need the score function, so which is the conditional probability for Y, given each X. So note that in general, that's not a one-hot, because it's not a label, it's a probability vector. You can understand it's the normalized logics after taking exponential, right? So once we have this base score function, and then the optimal price we have to pay is a generalization of the previous case. So the only difference is now we're using the so-called optimal transport distance, or the Wasserstein distance, to characterize the price. Wasserstein distance is strict generalization of the TV distance from the deterministic case to the stochastic case. Okay. Again, we don't have any analytical solution to the optimal price we have to pay. And the price we have to pay is the optimal value of this optimization problem. But luckily, again, this is a linear program. I won't talk too much detail about why it's a linear program, but it's a well-known fact in the literature of optimal transport that if you want to solve for the Wasserstein distance, that's a linear program. Now, once we solve the linear program, we also get the algorithm. And the algorithm is, again, a two-step procedure. So the first step is I want to find a barycenter similar to the TV distance case of multiple distributions. Now, the only difference is in the TV distance, each distribution is just a single point in the probability simplex because it's a deterministic label. In the case of the Wasserstein, each base score function is not a deterministic label, it's a randomized label. So that means we are starting from density over the simplex itself. And I have multiple densities, one for each group. I want to find another density cube to minimize the distance. That's the barycenter problem. And then once I find a barycenter, the transportation problem will give me the optimal post-processing rule. So that means once I find a barycenter of all the distribution, I will use the barycenter to partition the probability simplex into k groups. Suppose I have k classes. And all the point mass within each group will be transported to the corresponding vertex. And that's the post-processing procedure. So that means originally you make a prediction according to the base score, which is a strictly interior point, so where the probability simplex, right? Because it's a probability vector. And then because I already find a partition, the probability simplex, I will just transport the original prediction to the corresponding vertex. And that's the optimal solution. So for now, hopefully, I finished the discussion about what's the solution to achieve fairness and optimality in the most general case. And I want to briefly talk about some empirical results of this algorithm. And we applied our algorithm over a very standard benchmark data set. In the literature, it's called the adults data set. The task here is about income prediction, a binary prediction problem. And the data is come from the 1984 US census data. And here, each figure corresponds to a trade-off between fairness and the accuracy. So the x-axis means the violation of fairness. So if the value is smaller on the x-axis, that means a more stringent guarantee of fairness. If it's a 0, that means exact fairness. The y-axis corresponds to the accuracy. So the higher, the better. You see that in general, there's indeed a trade-off, meaning that if you allow more relaxation of fairness, you get better accuracy. If you're asking for strict fairness, then you have a drop of accuracy. But since it's a Pareto frontier, I want my point to be on the top in the left part. That means for the same fairness constraint, I get better accuracy, and for the same accuracy, I have better fairness guarantee. And we compare our method, which is the purple line, opposed to other information theoretic approach using projection in the literature. And it turns out, indeed, as verified, as claimed by the theoretical results, our product round is a strict dominance of the existing approach, mainly because of the optimality guarantee. And although in this talk, I mainly focus on the classification problem, but actually there's a similar problem for regression. And very interestingly, the optimal solution and the fair regression is again given by a barycenter problem. The only difference is in classification, we're using either TV distance or Wasserstein-1 because we care about the classification. Now, in the regression case, we're using the L2 distance of Wasserstein-2. That's because for regression problem, we're using mean square error. And optimizing for mean square error will give you the L2 Wasserstein distance. And by solving the L2 version for Wasserstein-barycenter, we can get the optimal prediction distribution, and then the transportation plan will give us the optimal post-processing map. Okay, so for now, I think I finished all the discussion so far. And I want to especially thank my student, Richard Shen, without whom it's not possible for me to conduct this line of research. And also thanks for all the funding agents we received from industry as well as from the DARPA government agency. Okay, so I think I finished my discussion so far. If you have any questions, feel free to ask now.
Any questions? I have some questions. So I guess throughout your talk, you made the point that there's going to be a trade-off.
Yeah.
But now, what if this sensitive attribute is really not something that has any causal relation to the I guess the thing we want to predict?
Yeah.
And really, like dependencies on the sensitive attribute are really just spurious correlation. So I guess my question is it possible from a causal learning perspective to argue that in fact here, we're not incurring a trade-off, but we're actually improving the overall accuracy?
So that's a great question. So it goes back to the slides here. So here the trade-off, when I use the difference of base rate, it's actually with respect to the true distribution, the causal distribution. But if you measure this term from your training data can be biased. And if you compute this term from training data, it can be non-zero. But that doesn't mean it's a trade-off. So here, when I use the difference of base rate, is with respect to ground truth causal graph in the context of causal setting. So in that case, if indeed there's no correlation between A and Y, then the difference of the two will be zero.
Okay, so causal relations, I guess there could be some classic dependency. So it could be the case that we have some underlying distribution that has some correlation, but it's not a causal one.
Yeah.
Still. So then just saying that I guess we've got something that's optimal with respect to the true underlying distribution, does not necessarily mean that it's still like optimal from a causal perspective, because I guess from a causal perspective, there would still be the question that, okay, if I change the sensitive attribute, would that have an impact on the thing we're trying to predict? And if the answer is no, then there's no causal.
Yeah, I understand the point. So I think more precisely to answer the question, I shouldn't use the conditional probability here. I should use the do operator. So if I say do A equal to 0 and do A equal to 1, the same one holds, but that is more precise answer to your question, because that corresponds to a controlled version of the ground truth distribution. Now, because in that case, there's no, if I perform the do operation, there's no confounder anymore. Yeah. So actually the proof itself extends to whatever the definition is we apply to the underlying graphic model. It's just the interpretation. So that's also one thing I want to mention, that one key is we shouldn't directly measure this term from potentially biased data, because you just measure this conditional probability from observational data which are biased, and then this term is non-zero. But that doesn't mean there's a fundamental trade-off. When we calculate this term, we should take into account all the potential confounder and apply the do operation. When we apply the do operation, I mean, we are performing a randomized experiment to measure this term. Yeah, that's a great question.
Okay, but I guess have you explored this, or is this?
No, I haven't explored this from a causal perspective, mainly because I'm not very exactly familiar with the causal techniques in the causal literature. But there are other researchers in the field. They try to tackle the problems from causal perspective, and what they found is you can actually further decompose this term into multiple parts. One of them is the fundamental part because of the causal impact of A to Y, and the other parts are through like an indirect link from A to Y in the underlying graphic model. But the main thing, difficulty of using causal approach to tackle the problem is we do need to make an assumption about what's the underlying structure. So what's the graph structure of the base net or the causal graph, which is unknown and non-identifiable in general. So that's the main difficulty. Yeah.
Any other questions?
So, I guess for the, so in the beginning, you said that, we have this constraint where you, have two label distributions and the error between them should be S equals epsilon. And then you had another, constraint, I guess, in the beginning, that said that the mutual information, should be, equal to zero. So are these mathematically equivalent?
Yeah, so if the mutual information is 0, you can just say that the constraint. If you just plug in the definition, except in the general case where the probability of A equal to 1 is 1, 0, meaning that as long as the positive ratio for each of the group, the mutual information equal to 0 implies you have exactly the same predictive diffusion. So on the other direction, that's not precisely true because you can have two fully dependent random variables. So if you have a Gaussian X and then the other variable is negative X, the distribution are the same, but the mutual information is 1. So that's not exactly the same. But in practice, what we start from is a joint distribution, as long as that joint distribution is not degenerate, in the sense that the Lebesgue measure is strictly larger than 0, then they're equivalent. So mathematically speaking, in the general case, these two are not equivalent. But as long as we make a small assumption, say the joint distribution itself is fully supported, then they're equivalent.
So by solving this case, you're solving that case as well.
Yes.
So I guess you indicate that I guess it's good to do some post-processing to I guess improve the fairness and so on. And we'll see how that's obviously convenient for lots of settings. Now, is there any loss in doing it in terms of post-processing versus doing it from
in process?
Yeah, from the start. Like at the beginning, you had some optimization problems.
Yeah.
You define like what you would mean both optimal and fair from the start. So like,
right.
Are we using
Right. So there's a key assumption in the general case in order to achieve optimality and fairness is because we need to assume our black box predictor is base optimal group wise. So that means the quality of the post-processing procedure highly depends on how good the black box predictor is. If the black box predictor is not good enough, then using our post-processing procedure will lead to approximate notion of fairness and also does not achieve the optimality. But we don't have control for that part using post-processing method. But if you're using in-processing method, you have the freedom to design whatever complex or powerful model to use. And that way, we do not need to have the assumption that we start from the base optimal group-wise predictor. So that's the trade-off here.
Yeah. So there are no further questions.
Okay.
Thanks
everyone for trying the thought.
Also, just want to remind everyone, so at 3 p.m. this afternoon.